Remember that when light strikes a mirrored surface, it reflects off the surface according to the law of reflection. So it's going to reflect off this way. And the law of reflection tells us that the incident angle, the angle between the incident ray and the normal line, is equal to the reflected angle, the angle between the normal line and the reflected ray. Well, we have one ray coming in, one ray going out. What we want is two rays to somehow combine together. Well, we can do that by adding a very thin film of material on top of the reflective surface. So let's imagine we've got this thin film of some other material on top of our mirror or on top of whatever the reflective surface is. Then, if we have a ray coming in that strikes the top surface, what does it do? Well, it will refract and reflect. So we'll have part of the ray reflecting and part of the ray refracting. The refracted ray will then hit the mirrored surface and reflect. That ray will then strike the top interface. That ray will refract and reflect. So it will refract and reflect. But remember, every time it reflects off the surface, we're going to get less and less light. Some of that light refracts, some of it reflects. So the reflected ray is lower intensity than the incident ray. And then this one, when it refracts, the reflected ray will be lower intensity again than the incident ray. So every time it goes up and down and up and down, it's going to get lower and lower in intensity. So we've got these two rays initially, these two first rays coming off of the material. But you might think, well, but they're not on top of each other. How are they going to combine? Well, no ray is actually infinitely thin. You might think about this ray as being part of another ray coming in next to it that will reflect, refract, and then actually come right back out on top of the first reflected ray from this source. So we've got two parts of the same incident light source coming in, just reflecting and refracting off slightly different places, but then eventually coming together on top of each other so that the electric and the magnetic fields can combine, either constructively or destructively. Now, what's the difference between the first ray and the second ray? Well, again, the ray that refracts first is going to have a path difference from the ray that reflects off the top. Now, the path difference is going to depend on what that angle is, because we're going to have some incident angle, and then we'll have a refracted angle, and the actual distance that it travels further than the top ray will depend on what that angle is. Well, that's very complicated. Let's make it simple for us. Let's imagine that we're actually talking about a ray that comes straight in perpendicular. Part of that will then reflect off the top surface. Part of it will travel in, reflect off the bottom, and then refract off the top surface. So these two rays will be back on top of each other. So we'll assume that we're talking about near normal incidence. So we'll assume that the ray, the initial ray that's coming in, is near the perpendicular. So we don't have to worry about this angle. It will at least give us an approximate result for what's going to happen here. Okay, so I've enlarged our drawing here. We've got our incident ray reflecting off the top surface, refracting into our thin film, reflecting off the bottom surface, and then refracting off the top surface. So what's the path difference between these two rays? Well, the ray that goes into the material has to go down and then up before it rejoins the original ray. So the path difference between the two is 2 times the thickness of the thin film. We'll call the thickness of the film T. So the path difference between the two is 2 times the thickness of the film. Now, how many wavelengths is that? Well, we need to figure out how many wavelengths before we can determine if it's going to be back in phase or out of phase. But the wavelength is actually the wavelength in the film. Remember, this is the film. What is the wavelength in that liquid, assuming that it's a film of liquid? Well, the one thing we do know is as the wave comes in, the wave, think of it as the frequency of the wave tells us how many oscillations of that wave hit the surface per second. When that wave hits that surface, we're going to have the same number of oscillations going into the film per second. So the frequency of the wave outside the film is going to be the same as the frequency of the wave inside the film. Just think about it in terms of that's the number of oscillations per second coming to the surface. That's got to be the same as the number of oscillations going into the surface per second. So the frequency up here has to be the same as the frequency down here. So the frequency of the light in the air has to equal the frequency of the light in the liquid. But we know frequency is equal to the speed divided by the wavelength. So in air, that's going to be the velocity of light in air divided by the wavelength in air, while the frequency in the liquid will be the speed of the light in the liquid divided by the wavelength in the liquid. So multiplying by the wavelength in the liquid and multiplying this, invert this, we get the wavelength in the liquid is equal to the speed in the liquid divided by the speed in the air times the wavelength in air. Now we know the speed in a material is c over its index, and so the velocity in the liquid will be c over the index of the liquid, and the speed in air will be c over the index of air. Now we know the index of air is very close to 1, so we'll just call that 1. The c's cancel, so we end up with lambda, the wavelength in air, but in air we know because n is just about 1, that we'll just call that the wavelength. It would be about the same as the wavelength in a vacuum. So we'll just call that lambda over the index of the liquid. So we end up with the wavelength in the liquid is the wavelength in air, or the wavelength in the vacuum, either one, divided by the index of the liquid. So what we need to do is compare that path difference, 2t, to the wavelength of the liquid. However, there's one more thing that we have to take into account. Let me do a little demonstration and we'll take a look at it. Okay, so I'm afraid my lovely assistant Fred has bailed on me, so I have asked my lovely assistant Kathy to assist us here. What I'm doing is I've got two different slinkies, and we're going to send some waves through them like this, okay? Now, the metal slinky is stiffer than the plastic slinky, so we can kind of think of this like this is a medium with a higher index, a larger value for n, while for the plastic, that's like a medium with a lower value for n. Now, I'm going to send a wave down, and the first thing I want you to notice is that in my wave, I'm just going to move my hand like that. I'm going to send a wave down, and I want you to notice that it goes from the metal into the plastic. Okay, so you can see that we have a transmitted wave. Likewise, if we have a wave in the plastic, we also get a transmitted wave into the metal. Okay, do you see that? So it transmitted into the metal. So from the plastic to the metal. So from metal to plastic, plastic to metal. Now, I also want you to notice that we get a reflected wave. So when I send a pulse down and it hits the interface, not only does some wave go into the plastic, but some wave is reflected. So I want you to notice that there's actually a part of the wave that gets reflected once it hits the interface. Right there. Did you see that? Do it one more time. There, right there. That was the reflected wave. Now, the same thing will happen with the plastic. There. Did you see the reflected wave? Once it hit the metal, there was a wave that was reflected back. Now, there we go. Okay? Now, there's something else I want you to notice. And that is, on what side is the reflected wave? I'm going to move my hand to my right, which would be your left. I want you to notice that the reflected wave also comes back on the right side, your left side. In other words, the same side when it strikes the surface. Ready? So watch for the reflected wave and notice that it's on the same side as the initial wave. There. Did you see that? Do it one more time. There. See? It's on that side. However, the reflected wave in the plastic comes back on the opposite side. So Kathy is going to make the wave on your right side. Notice that it reflects back on the left side. Did you see that? Let's do it one more time. And let's try one more time. There. Everyone see that? That's the important point. So let's go back over that. When a wave goes from a larger index to a smaller index, it reflects on the same side. In other words, there's no phase difference. However, when a wave in a smaller index reflects off a larger index, it reflects on the opposite side. In other words, there's a phase difference of pi radians, or 180 degrees, which is like, as we've seen, a half wavelength phase shift. It's like one of the waves had to move an extra half a wavelength. Great. Let's go back to our thin film interference. Thank you, Kathy. Okay, so we've got two reflections going on here. We've got the top ray that is in index N1 and reflects off index N2, and we have the bottom ray that is in index N2 and reflecting off the bottom surface, which let's say has some index N3. So we've got a number of possibilities. If N2 is less than N1, there will be no phase shift for the top ray. But if N2 is larger than N1, we'll have, let's say, a pi radians phase shift for the top ray. If N3 is less than N2, we will not have a phase shift for the bottom ray. If N3 is greater than N2, we will have a phase shift for the bottom ray. Now, two phase shifts, two half wavelength shifts, is the same as a full wavelength shift, which is like no shift at all. So if we have 0 phase shifts or 2 phase shifts, that's essentially no phase shift. But if we have 1 phase shift, then we're going to have to change the way we look at this. So what we get is, with no phase shifts or both having a phase shift, 2 phase shifts, then if 2t, the path difference, 2 times the thickness of the liquid, the thin film, is an integer number of wavelengths of the wave in the liquid, lambda in liquid, then we're going to have constructive interference and the rays will add together. If 2t is m plus a half times lambda the liquid, then we'll get destructive interference. However, if we have only 1 phase shift, if one of the rays has a phase shift, then those results are reversed. And then if 2t equals m plus a half lambda liquid, then we'll have constructive interference because that 1 phase shift will add an extra lambda over 2 to put them back into phase. Whereas if 2t is equal to m lambda liquid with 1 phase shift, then we'll get destructive interference. Now, have you ever seen anything like this? Well, I bet you have. One situation is a very, very common situation. Let me put up a picture of it. Have you ever blown soap bubbles? Well, if you have, or if you've ever seen soap bubbles, the different colors, the swirls of colors that you see in the surface of the bubbles, those are called by the interference of light bouncing off the inside and the outside surfaces of the film. Now, if you'll remember from our equations, whether you have constructive or destructive interference depends on T, the thickness of the film. Now, in these soap bubbles, the film varies ever so slightly as you go from one place to another, which means the wavelengths that will give you constructive and destructive interference change as you go over the surface of the soap bubble. Well, changing the wavelength means changing the colors. So, in one place you might get constructive interference for one color, but right next to it you'll get constructive interference for a different color, and then another color and another color. So as you move over the surface of the soap film, you see these rainbows of colors because you get different interference, constructive and destructive wavelengths. Another situation where you might have seen this is if you've ever been to a gas station and noticed maybe a thin film of gasoline on some water. You might see those rainbows of colors in the oil or gas or something as it's floating on top of the surface of the water. And again, because as the thickness changes, the different colors that will give rise to constructive and destructive interference change. And there is a great example of thin film, what's called thin film interference. Okay, well great. That finishes up for today. I hope you enjoyed that. We'll see you next time.